Good afternoon. It's a great pleasure and honor to be here. And I'll talk about the 21st century computing. And before we start, I just want to mention that we, humankind, are actually tool makers. What we are doing, and that's unique for humankind, is that we create tools, we make tools that amplify our natural capabilities. And these tools are everywhere. It's in the transportation, it's in communication, and every new tool amplifies our abilities and actually creates appetite for even more. And this appetite drives the development of new tools and so on and so forth. And one of the most important tools that have been developed by human now is computing. And it was first computers were designed to crack the German code. It was in the Second World War, and these computers were very hard to use. Thomas Watson, who was the IBM president, didn't believe that the market of the computers is more than 5 units annual, or worldwide, sorry, not annual. But eventually computers get more and more usage, and as a result, more people used it, and more people used it, so we developed tools to make them simpler to use, like operating system, like programming languages, like compilers. And then PC revolution came in, even more people started to use computers, so even more people develop applications, and even more people develop applications, and more people use computers, and this invention of operating system and standard application interfaces actually enabled to carry over the software investment from one generation to another. The next one was the internet that actually combined two important technologies, communication and computing together, which was yet another wave of development. And then computers were developed more and more, and the internet, along with the more compute power, started to build the data centers, which is actually factories that delivered the computing and storage as a service. So if you think about the computer, is not like a box under your table, but as a service, like an electricity, that you can consume the electric power from the electric plant out there. Now you can consume the computing power out of these data centers. And mobile and mobility actually drove even additional things over there, which is huge amount of data. All of us are actually generating data, carrying our phones, taking pictures, videos, location, and so on and so forth. And this enabled us to tackle the new challenges. The von Neumann machines, which is the traditional computers, were evolved and developed, and they could crank and deliver quite a lot of complex. We could write the programs that solve quite a lot of complex problems. And programming von Neumann machine is actually like telling somebody what to do, step after step, so explaining. It's like I can explain you the algorithm, I can explain it in C or Fortran or whatever language it is, and then computer will execute it. However, there are some things that it's really hard to explain. It's really hard to explain how to distinguish between cat and dog. Imagine that you are trying to explain to someone that never seen cat or dog how to distinguish between them, and then show him cats and dogs and expect that he would actually identify correctly what is the cat and what is dog. But on the other hand, 3-year-old kid can fairly clearly distinguish. And how does he do it? Because he has seen many times cats and dogs, and he was told which one is cat and which one is dog. And therefore, there's a new computing model, a new way of programming or creating the programs is invented. It was developed, and it was inspired by learning of the human brain, the brain structure, and this is a neural network model. So the neural network model is the computing model that actually uses the data to improve the results. So it is fairly what's called neural network. It is combination or collection of very large amount of very simple computing elements that each one has its own parameters. And by showing this neural network pictures, images of cats and dogs, you can actually tune these parameters by a lot of computation involved and identify who is the cat and who is the dog. And after you've done enough training, this machine will actually be fairly good at the image recognition. So that's where the first time the parallel computing, highly parallel computing, met the demand and met the requirements of a much wider audience than just government serving high-performance computing. So image processing is something that started in 90s or maybe even in 80s. So image was really easily translated. There was technologies to translate the image to numbers, the pixels, and therefore we could feed the computer, which only thing he knows is to operate the numbers, is to do the things. And once this started, then we created of course, everything needs to be measured. So there is created a benchmark called ImageNet, which is hundreds of thousands of images that you need to classify, the one that under the test needs to classify. And the classification error, it's how many misclassifications, so there's cats, dogs, different kinds of cats, and so on and so forth, and you need to classify all of them. And it started with the fairly high classification error of like quarter of the cases the machine was wrong. But a few years later, machine actually has a computer vision becomes better than human vision. The average error of humans on this type of benchmark is about 5%. In 2015, computer built actually by Chinese company Baidu using Mellanox technologies and NVIDIA GPU became better image classifier than humans. So computer now has ability to understand pictures. So the next challenge is to understand human language. So how can we make computer to understand human language? Okay, first of all, you need to convert the word to numbers. Computer can only work on the numbers. So how do we convert word to numbers? What we do, we create, we say that each word is represented in by multidimensional vector. And you can think about that when you explain the word to somebody that haven't seen it, you say, no, it's like a man, it's like a woman, it's a tree. There's a lot of characteristics on each one of the words, and actually we made the computers learn about the words by feeding it pretty much the same way as we human learn the language. If you meet the word that you haven't seen before, you sort of guess its meaning from the context, then you see this word in a little bit different context, and then you basically refine your understanding what does this word mean. And the way machine learns language is that you just feed the machine with a text from Wikipedia, petabytes of text. You feed the machine, you let the machine guess for every word, which words are surrounding it, or for surrounding words, you make the machine guess which word which is missing in the sentence, and you tune these parameters of each word so to minimize the error. And at some point, you can think about these words, and you can do it for any language. It's actually done for any language. And you can make the machine understand the meaning of the word, and not only understand meaning of the word, but actually also understand the relation between different words. Here is the two sentences. I cross the river to get to another bank, or I cross the road to get to another bank. And so there is only one word difference in these two sentences, and it changed drastically the meaning of the word bank. And so what does word bank mean in the sentence in the first one? And what does the word bank means in the second one? Okay, so you go to ChatGPT and you ask the question, and it tells you that the word bank in the first sentence means it's the bank of the river. Keep in mind, though, that it may be a bank of financial institution, but in this context, it sounds like a bank of the river. When you ask about the second one, the answer is much more definite. There's much less hesitation, or the hesitation is not worthy to mention. And why is that? Because if you think about this multidimensional space where all these words are represented by these numbers, it's like every word is a multidimensional vector. The word bank is near in this space to the other words that has to deal with the financial institutions. But the word river is also somewhere there, not as close as financial institutions, but not very far away. And by being present in the sentence, it actually sort of skews or drags the meaning of word bank toward the river. So we managed to machine to understand the language. We managed the machine to understand multiple languages. We managed the machine to understand images. And you can think about this, that this machine gets multiple things that he's able to understand. He knows to understand. It is images, it's video, it's protein language, it is different human languages, it is images, and so on and so forth. So it sort of creates an insight out of this data, out of these things that he was fed into. And this insight can be expressed by not necessarily the same way as it was generated. The simple example, I can see something, and then I can draw the picture. Well, I can draw the picture, but I'm not capable of doing this. But on the other hand, I can see picture, and I can explain in 3 languages that I speak what is in this picture. I can hear something on one language, and I can translate it to another language. And this actually creates an opportunity to look at another capabilities or another feature that we are a human possess that not other creatures possess, is the ability to communicate. Humankind is actually ruling the world because of our ability to cooperate, and this cooperation is basically stated on the communication. And we were enhanced this ability to communicate starting from printing, then telegraph, then phone, and this video. And each one of these steps were fairly significant change from one to another. From printing to telegraph, it's the time to communicate. From telegraph to phone, now you can hear the intonation. You can hear the music behind the voice. Video conference, now you can actually see my counterpart. I can read his body language across the ocean on very high distances. And the first video conference was done in, I think it's in 1964, AT&T, the first video conference. And since then, all this communication was focusing, or enhancement of this communication, were focusing on better data compression, better video. So the idea is to present on the other side of the communication line the picture of the image to be as close as possible on the other side. However, it's not always necessarily the most efficient way to do. Okay, one of the simple example is that, you know, if you speak one language and you send it to the other side of the ocean, then you hear the same language, but not necessarily understand it. Body language, not everybody understands the same figures and same body language the same way. So if we put in between two sides of the communication, ability to translate, to transpose the message from one side to something that other side can understand, we can actually make this communication empower from being the communication carrier to actually empower our communication. I can give you a simple example, you know, besides, you know, just trivial example like translation, which exists today. I just read that Google earbuds can use the services to translate languages. But that's actually even more than that. You can translate human language, body language, sorry. Today we are using Zoom and other video conference quite a lot from home. And when we started to use it extensively started to use it in the beginning of the pandemic, when everybody worked at home, one of the weird things is that when you talk to somebody, and I'm not talking about the big conference where a lot of people there, but if I'm talking to somebody, I expect him to look at me, and I look at him, right? But if you talk with somebody over the video, it either looks sideways or down or up, but never at you. And the reason is because he's actually looking at your image on his screen, but his camera is not on the where your image is. It's either up screen, down screen, or sideways. So it's weird. Now, in the NVIDIA, we actually developed the driver that fixes the eyes. So you can, when you use this driver on the way that, well, unless you are really looking sideways, but if your camera is somewhere around the screen you are talking to, the software will actually put your eyes in the right place. Another example, I don't know if probably many of you talk to India. So if you ask here, if you understand what I'm saying, you will probably say this. If you don't understand, you will say this. In India, it's the other way around. If you talk to somebody and he moves his head sideways, it means he is really comfortable with what you're saying. If you talk here, if somebody moves his head sideways, when you talk to him, it means something different. So you can apply the AI to customize the message so the other side will better understand what you are saying. It can do the revolution in the education. The teacher is talking to 20 people in the class, and not necessarily everybody understands what he's saying the same way. It can do better communication on the 5G companies are using their data centers and using their equipment to enhance communication. Real-time language translation already exists today. So we can make the communication, which is the key thing of people being able to collaborate, much more powerful and being empowered by this technology. So it's all cool, and we can go to ChatGPT and ask the queries, and it will get the great response based on the data it was trained on. And data it was trained on, it's publicly available data, and you can get a lot of things, cool things together out of there. We can ask the machine questions. We can ask the machine to write the program, and it will generate the code that we can run on the computer. But what it cannot do, it cannot work on the data that is not there. So there is a great capability on one hand, and there is my personal data on the other hand, and I want to take this and this great capability and deploy it on my own data. So how can we do it? Okay, we cannot afford to buy or to build the large language model ourselves. It took 10,000 GPUs in Azure and the OpenAI to train the ChatGPT. But what we can do create our own database and encode it and make this machine to work, to use this capability of ChatGPT or any other large language model to the data that it was not trained on, but on the data that was created locally. That's the way, by the way, all the chatbots are working. At NVIDIA, I'm talking to people from time to time, to new hires, and the common complaint or common note message is that it's really hard to get the knowledge in terms of documentation is not quite available, and it's available, it's not structured, and you don't know whom to ask, you don't know where to look for. So we said, let's take all our documentation and make large language model to apply its capabilities on this documentation. Actually now nobody asks the question. You just go to our this interface to the large language model and ask the question on the NVIDIA technology and the products, and you will get the answer, and it's actually without exposing the real context of this information outside, because it's encoded in the vector database that we create. I actually did it at home on all the open tools, not going to some secret sources of NVIDIA. And I created this pipeline by writing Python code on my PC, on my laptop. By the way I wrote this code is just ask ChatGPT to write the code, and it did it. And what I did, I created the database of my camera, photo camera, and then I started to ask questions, how to connect my camera to my smartphone. And it lists me the steps you need to do, although it's not explicitly written in the manual. My wife was very excited about it, and that's, by the way, warning about data that you feed these machines. Excited about it, so I put all the manuals that I have, the PDFs, to this database, like from the washing machine and from the dryer and for everything I had. And then I asked the question, how to replace battery on my camera. And it said that first thing you need to do, you need to empty the washing powder from your camera. So when you feed these machines with the data, sometimes it hallucinates, and you need to know how to feed the data, how to ask the question. And that's, by the way, yet another capability of prompt engineering. You need to know how to ask the question. Okay, so all these developments drove dramatically the demand of the computing. The model size, the number of parameters of the model were growing dramatically with the transformers, with the models, and when transformers models came in, that's the heart of ChatGPT, the growth of the models even accelerated. So instead of going, 8x every 2 years, then it started to run 150x in the 2 years. So model gets bigger and bigger, 150 times every year. So a number of parameters growing, which basically drive the requirements for computing and for storage. And as I mentioned before, the new demand comes in, and new solutions come in, and it's like a law of nature. Whatever we will need, we will figure out how to get. So the traditional or PC era computing power was growing based on the Moore law, which is getting, enabling more and more and more transistors for that can be packed on a single device. And this law was not good enough, was not powerful enough to deliver this performance growth. So we had to go all the way up and innovate not only on the bottom, which is very convenient because once you innovate on the bottom, everything up there benefits it. But you need to go all the way up to the stack, all the way up to the application. So you need to accelerate the application. We need to restructure the application because we need to invest in software, compiler technologies, algorithm technologies. We need to build domain-specific accelerators because general purpose computing is great, but because of the general purpose, it can do everything, but it cannot do anything absolutely perfect. So you need to accelerate the domains that really requires and demands much more computing, and you need to invest in the algorithms, in the new way of transforming the data to information, in the new way to create the applications. And all these things together actually enabled the growth of that was demanded by growth of the models. So accelerated computing is something that actually NVIDIA started accelerating the graphic processors for consumer market. And that's where NVIDIA technology of highly parallel processing met the needs of large and high performance and high scale computing. So we don't accelerate a single machine, a single CPU, we accelerate the entire data center. And what happens as a result is that when we program our von Neumann machines, we basically write the code, which is writing on the simple. You don't need a lot of power to type the code. Then you compile this code, and then you need a really high performance computer to run this code. Okay, you do the code for fluid dynamics or some other simulation things, and then you need very fast machine to run the code. With the neural network model and with the AI technologies, it's actually other way around. You need a lot of computing to train your neural network. You need a lot of computing to process the data to have these neural network parameters fit or tuned to give you the right results. But then you can prune the network, you can degenerate the network, so sometimes it can fit in the cell phone. So it is to create the application, to create the service, you need a lot of compute power. To run the service or to deliver service, or many of them, you don't need as much compute power as you need. So you need a big computer, much bigger than we built before. And what actually happens is that data center becomes a new unit of computing. That's where vision of Mellanox and vision of NVIDIA met each other, and that's why NVIDIA acquired Mellanox. And this big computer, as traditional computers had operating system, it had application tier, okay, then the same CPU was running both. And on this big computer, and the role of the operating system is actually manage the resources and present the application interfaces that we can carry over from one generation to another, software. So the data center computer, the job of operating system is much more complicated. And the security requirements and the barrier of the security needs to be much higher. So as a result, what we are doing actually, we built in Mellanox, we developed the DPU, which is data processor unit, and there is 3 pillars this data center computer is built on. It is CPU, traditional von Neumann machine, that also needs to be, by the way, optimized. That's why we build in NVIDIA, why we build the Grace CPU. We build our own CPU. We started with Intel. And the DPU, which is the data center processing unit, that's the platform to run operating system of the data center. And GPU, this is actually the machine that cranks the data. This is the heavyweight processor. So with all these things, we have managed to deliver to satisfy the requirement. And unlike the PC world, where the computer were getting smaller and smaller, here we cannot satisfy or meet the demand of the computing, and actually computing getting bigger and bigger. If supercomputers or large computers in the previous millennium, we were talking about maybe a rack, maybe 2 racks, the computers. The computers that we build today are hosted in the building that they can fit 2 Boeing airplanes. So it's not something that you can easily put on your labs, right? So that's where we are today in terms of meeting this demand, and we are looking forward to even higher demand. And one few notes about the acceleration is that accelerated computing is really required to sustain, to have this computing sustainable. Today, data centers are consuming about 5% of global energy on the planet. And if we don't take care about this, we will not have enough electrical power to feed these machines as needed. So what can accelerated computing do for you? As a reference, if you need to train one large language model using the best breed general purpose CPUs, it will cost about $10 million. You will need about 1,000 CPUs, and it will consume 11 gigawatt hours of power. Now, if you want to send for the same money for the accelerated computing, you can train much more models. But I put this just for a reference, because what real limiter today, it's either amount of power that you can afford to consume. Data centers are limited by the power and by their size, or how much do you want to spend to train one large language model for your enterprise. So if you are constrained by power, by the same power that you need to train large language model, one large language model on a general purpose computer, you can train 150 large language models for the same power. And if you only need to train one LLM, then by fraction of the power and fraction of the cost, you can do it in much smaller space. By the way, space is yet another limiter. Today, the development of the computing is actually limited by time it takes Conquer to harden when they build the data centers to host these machines. So the AI factory is, today we build factories that actually translate data to information, generate intelligence. It took, and GPT-3 is one of the products that were delivered by this factory. And by the way, it took 323 zeta flops to train ChatGPT. Zeta is 1 and 21 zeros. So it's a lot of compute power that was needed to train ChatGPT. And the network, by the way, is the real nerves of this big computer, big machine. So we have a GPU that crunches the data, CPU runs the framework, application, and the DPU is the operating system platforms, and the network is the nerve. Now, this type of technologies enables us to build the simulators of much larger entities and much larger things. Okay, you can simulate huge projects. I've renovated my apartment a few months ago, and in the last days of this renovation, there's a lot of bugs uncovered, and my wife was sort of telling the constructor what does he think about this, and this constructor came to me and said, you are building the very large project, so why you guys don't understand that there may be bugs that you need to redo the project? I thought, in the projects I'm doing, every bug fix is $50 million. And there was about at least 10 bugs discovered that day by the constructor. So if I would be running my projects the same way he does, I would go out of business fairly soon. And then I thought that, we are not out of any other genetic pool. These guys are as good as us. So why they cannot make their stuff to work on the first shot? And the reason is that we are simulating our projects to death before we start building it. We're simulating our chips. The chip has, 500 billion transistors. Every transistor needs to work, and we need to be in the right place 100%, not 99.99999, because otherwise it's not going to work. It has to be right in place. So we simulate this to death. And actually, we can build with these huge factories, we can build the simulator that simulates the physics in the real world. And we have customers that are actually doing this. The Heavy AI, they use Omniverse, which is NVIDIA platform, to create virtual worlds to enable their customers to, for example, place the 5G equipment. And this Omniverse platform enables to simulate the real world and the real buildings and the real structure and the real weather in a way that they can optimize placement on their equipment, so to deliver the service at the most optimal cost and most optimal way. Another example is Deutsche Bahn. It's actually making their railway services much more efficient by simulating it. We have a simulator of our own data centers. We simulate data centers in this digital twin of the data center, and we develop technologies and develop our data centers based on these simulations. We can do the trial and error, adding new capabilities and new equipment, and how to enhance our operations and how to protect them, by the way. We do these digital twins, and we analyze the data that we feed these AI models to do for predictive maintenance. We have a capability that we developed that can predict the failure of the cable, that can predict the failure of the GPU, that can predict the failure of the rack. So it tells you, 2 hours from now, this rack will most likely fail. So you don't need to wait till it fails. You just gracefully migrate the applications running on this machine to other machine and take care about the broken equipment. So sometimes people ask me, what is next? What else is coming? So the data center is the computer, and the accelerator for this computer can be a quantum computer. The quantum computer is the new type of data processing that is very cool and promised to be very efficient for data crunching, not as good for data processing itself, for large amount of data. Quantum computer, and that's a matter of whom do you talk to. I believe it's 2, maybe 3 decades away. But every quantum computer will need to have a conventional computer next to it, because like every GPU has the CPU next to it. And but once you have this quantum computer, you will need to restructure your problems, your algorithms again. Like you had to restructure your algorithms and your software to take advantage of the GPU. Now, once quantum computer is there, we need to restructure our algorithms to take advantage of this new type of data processing. And we at NVIDIA we don't develop quantum computer per se, but what we do have a simulator of the quantum computer, and we have a framework that enables developers to restructure the algorithms that actually enables them to simulate the data center computer with the quantum computer as accelerator. So once the quantum computer will be there, hopefully we'll have enough enough programs and enough applications, enough services that will take advantage of this accelerator sooner rather than just starting developing this. Because today, all the algorithms are built how to work around the problem that can be solved straight ahead on quantum computer, but cannot be solved on the conventional computer. So that's what we are doing. We are basically accelerating the quantum advantage. And once the physicists and the people that are building quantum computer will have it ready. Oops. Okay, works. Okay, so that's what we develop to enable people to take advantage of the quantum computer. So once you have a quantum computer, you need to have of course, traditional computer, normal computer, data center itself next to it to feed it with the right things over there. So just to conclude, today these days it's the iPhone moment of AI. And it is actually democratizing the computers. So now everyone can be programmer. I was telling ChatGPT to write me the Python script, and it did it. So you don't need to be PhD in computer science, and you don't need to take multi-months classes to know how to program the computer. Before ChatGPT, before generative AI, everyone could consume the compute services thanks to these advanced developments of PCs, iPhones, and so on and so forth. But what iPhone enabled is to enable to have a different way of consuming the computing services. And what generative AI enables is to everyone become a creator of the computer, of the services based on the computer. Everyone can program the computer. You can just tell the machine what to do, and it will generate your code, what you need to do. Machine will understand what you mean, and you can do not only create the new applications, you can also do a lot of good things for old applications. It's a browser, it's a PowerPoint, it's the communication that we talked about before. And it is very, very easy to do. I'm pretty sure that all of you tried ChatGPT, and it's amazing how easy to use it and how the quality of the results that you are getting. So, looking forward for great future. I'm not among those that concerned about technology that it will do bad for us. It will do good for us because that has always been the case. And that's pretty much concludes my talk. I'll be around for a break and for gathering later on. So if you have any questions, welcome to ask.